atomic theory. Like I said, this is actually one of my favorite chapters. So we're going to figure out like how we figured out what atoms were. So we're going to talk about Dalton's atomic theory, the structure of the atom, and then ions and atomic mass. By the way, this lecture, you won't need your calculator, but next lecture, so next Tuesday, you're going to need your calculator. Okay, so first thing, Dalton's atomic theory. So this is 1800. This is quite a while ago. So Dalton said a few things. So yes, I think this is being recorded. Let me just check. Yes, this is recorded now. Okay, so he said that, remember, this is couple hundred years ago, right? He said that all matter is composed of small indivisible particles called atoms. And then he said that atoms of a given element are identical in both mass and chemical properties. And atoms of different elements have different masses and different chemical properties. Okay, so what that mean? So he's saying that, so if you have a piece of iron, every single, in that piece of iron, are iron elements, and every iron element, every iron atom is exactly identical in both mass and its chemical properties. And then you have, let's say, oxygen over here, right? Oxygen, every atom of oxygen is identical in both mass and chemical properties. And now he's just saying that atoms of iron are different than atoms of oxygen. And we're like, yeah, duh, right? But you have to remember, in 1800, this was a radical idea, right? Even to propose that atoms were a thing was crazy. And to say that iron is different than oxygen, again, very different. The other thing he said is that atoms are not created or destroyed in chemical reactions. Again, this was like crazy back then, right? It's just, all he said that they were rearranged. And this now is our law of conservation of mass, which we'll talk about a lot soon. Probably next lecture we'll talk about it. The next thing he said is that atoms combine in simple, fixed whole number ratios, and they form compounds. Now, what does this mean, simple, fixed whole number ratios? So, for example, we talked about this a little bit. CO2, right? This simple, fixed whole number ratio. And so we can only, this is one carbon and two oxygens, right? It's not a half a carbon or 2.5 oxygens. It's one carbon, two oxygens, and the ratio is always one carbon to two oxygens. And again, to us, we're like, yeah, of course. But back then, this was kind of a crazy idea. Okay, so this is Dalton in 1800. And so we kind of had our ideas of atoms. And again, here's what he said, that these atoms, so here's our hydrogen and our oxygen, right, rearrange into new combinations. So now we're going to look at the structure of the atom. So we had Dalton in 1800 say, okay, here's what I think about atoms. And then we have to figure out like what's in an atom. So what we're going to look at is how atoms are different from each other, what they're composed of, and the subatomic particles, and how we even figured those out. So most of us remember this piece, right? Maybe. We might have to like dust off the cobwebs, but most of us remember this. So atoms actually are divisible, right? So Dalton wasn't quite right by that. They are composed of these small subatomic particles. Now we know there's more than electrons, protons, and neutrons now, but we're just going to stick to those for our course. So one kind of particle outside the nucleus, those are electrons, and electrons are negatively charged. Inside the nucleus are protons and neutrons. Protons are positively charged and neutrons are neutral. So now we're going to talk about how did we figure this out, or who figured this out, and how did this happen? Okay. So let's look at electrons now. So remember, Dalton was like early 1800s. This is like 100 years later when we actually figured out electrons. And this is J.J. Thomson, and he's quite the character. And we're going to talk about him today. So J.J. Thomson used this thing called a cathode ray tube. Now, at the end of this, if you can figure out what this discovery led to, I'll tell you this, without this discovery, our lives would be drastically different. We would be, I don't know, depends on how you look at it, much sadder in our lives if you can figure out what this discovery led to. Okay, so he used this thing called a cathode ray tube. And what he did is he had a voltage like a battery and he applied it, right? So here's your battery. And what he did is he made electricity become visible. Well, you couldn't see it here, but what he did is he painted, you see this gray here? So he kind of painted the edge of this. And what happened was this electricity, you could actually see this dot. So you could see the direction of this electricity. Okay, and he had this specially coated glass. Seeing some of you guys already figured this out. Okay, so what he did is he put a positive plate on the top and a negative plate on the bottom. And when he did the same thing with the electricity, you can see now it bent towards the positive plate because he could see it on that specially coated glass, right? And so that means, because we all know that opposites attract, right? Like charges repel and opposites attract. You've probably experienced if you used a magnet, right? If you have a magnet and you try to put both like the same sides towards each other, it repels. And if you flip it, they attract. Same thing with electrons, right? So if the electrons are negative, that means that they should be attracted towards this positive plate, to the negative plate. Well, they were attracted to the positive plate, and therefore he determined that electrons must be negatively charged, right? So let's just review that again. So he had this electricity and this specially coated glass so he could see where this electricity ended up, right? Then he put two plates, a positive and a negative plate, and the electricity bent towards the positive plate. And that's how he knew that electrons were negatively charged. And that's where electricity, that's where it comes from. And I can see that some of you figured this out, right? J.J. Thomson should be your favorite person ever because yes, this led to the discovery of the television. Right? If you've ever seen those old tube TVs, like with the big fat backs and they're crazy heavy, you could actually, if you got close enough, see the little dots. So if anybody's ever seen those little old TVs, right? Like they're like little beams. Yeah, they have little particles and little circles. That's what JJ led to. Now let's think of what, because of the TV we have, right? Because of the TV we have, right? Without this, we wouldn't have our smartphones. Right? We wouldn't have movies.
We wouldn't have Star Trek.
We wouldn't have Star Trek, right? Think of all the things that came because of J.J. Thomson. Hence why I said J.J. Thomson should be someone, laptops, we wouldn't have computers. We wouldn't have any of them. Yeah, no TikTok, nothing without J.J. Thomson. So we should all be very appreciative of J.J. Thomson, right? Because he really did set up our future for us. Okay. J.J. Thomson was a little, like I said, he's kind of a character. So he figured out the electrons using the cathode ray tube. The next thing he needed to figure out was, so he knew the electrons were in the atom. And so he knew that there was because he knew atoms were neutral, he said there's got to be another piece that's positive. He called those protons. Well, J.J. Thomson, like I said, he was a character. I think he must have been like eating dinner one night and he had plum pudding for dessert, which is a popular dessert then. And he decided that the atoms are like plum pudding. And it actually became the plum pudding model of the atom. This is actually what it's called, plum pudding model. So what JJ decided was that the pudding was just a sphere of positiveness. And in that sphere of positiveness, there were these little plums of electrons. Think of it kind of like tapioca pudding, like the tapioca pieces would be the electrons. And some people are like, I've never had tapioca pudding, like a chocolate chip cookie. So like the chocolate chips are electrons and the rest of the cookie is just a sphere of positiveness, right? And this is what JJ decided that the atom was. Like I said, kind of a character. And so this is the plum pudding model of the atom. And this was in like late 1800s, right? And this was accepted. This was an acceptable model of the atom, plum pudding. Well, a few years later, Ernest Rutherford was like, JJ, I don't know about this whole plum pudding thing, right? And so he decided to create an experiment to test if the atom truly was like plum pudding. Now, What he did, and I'm going to show you a picture of this. So what he did is he bombarded gold foil with alpha particles. And to us, that doesn't really mean anything, but let me show you what that is. I'm going to show you a picture of it, and I'll come back to this. Okay, so here's what he had. So he had this radioactive sample, and this emits alpha particles, which are helium. They're helium atoms, but to us, they're helium nuclei. We'll talk more about what they are later. Just think crazy amounts of energy, like crazy amounts of energy. And then he hit them against, he hit gold foil with it. So it's kind of like if you had like a BB gun and you had a tissue paper. That's pretty much what he did. He's like, well, if I hit this gold foil or this tissue paper with a BB gun, the BB should go through it, right? And if that's true, then this plum pudding is true because look, it's mostly empty. So if you hit this, it should go through it, right? This is what should happen if I hit a BB gun against tissue paper, it should go through. That's kind of the basis of Rutherford's experiment, that if indeed plum pudding model was a correct model of the atom, then everything should go right through. Right? This is what should happen, right? But this is not what happened, right? So what actually happened is most of them did go right through, just like JJ thought, right? Like plum pudding. But some of them actually deflected back almost completely. So this would be like if you had a BB gun and you shot it at tissue paper and it bounced back at you, the BB bounced back at you. You would be like, what? Like, it would be almost indescribable. You'd be like, how can this possibly be, right? And some of them were deflected just a little bit, but some, again, deflected all the way backwards, which just made absolutely no sense, right? Because we thought the model was like plum pudding. So what happened was these alpha particles were expected to go right through our gold foil, and most of them did, but some were deflected slightly and a few actually bounced backwards, right? This led to the idea of a nucleus, right? And so because most of them went through, Rutherford decided, not we, because I didn't decide this, Rutherford decided that the nucleus must be really tiny, right? Because most of them went straight through just as expected. But some of them, those few that bounced right back, means that we must have a very hard, very dense, positive something in that atom. And that's what Rutherford called the nucleus. So this is, again, here's what happened. Again, most of them went right through. Some of them, though, had these major deflections, right? And that led us to believe that there's this nucleus that's very small, very tiny, very dense, positively charged. So here's what we, again, thought. If JJ was right, this should have happened. But it turns out plum pudding, not the correct model of the atom. So we hit it with the gold foil, and again, most went right through. Some had a little deflection, but the weird, strange thing, again, it would be like a BB bouncing off tissue paper would be crazy, but this is exactly what happened. And again, here's the bigger picture of what happened. And this led to, I'm just gonna go back here, this idea of the nucleus, right? And this also said that most of an atom is empty space. Again, most of it's empty space because most of them went straight through. So that means there was nothing stopping them. So most of them most of the atom is empty, but there's this hard, dense nucleus that made some of them deflect. And so Rutherford figured out the nucleus. And so we called that the Rutherford model of the atom, which stood for a very long time. And most of us, right, unless we've had chemistry in the last few years, still have that same idea of the Rutherford atom. He is very correct in many things, but we're gonna talk about and develop this idea on where these electrons are in the atom. Okay, so we figured out, JJ figured out our protons, right? And JJ figured out our electrons, figured out there were protons. Rutherford figured out that there was a nucleus, and that was the gold foil experiment. Then there was the neutron. We're not going to go into this one in like great detail, but we have to give him some acknowledgement. James Chadwick actually figured out the neutron. Ernest Rutherford knew there was a neutron, but he didn't actually prove it. But he said there's missing mass. But it was really Chadwick who figured it out. You don't need to prove Chadwick because, you know, neutrons aren't anywhere near as exciting as protons and electrons. Okay, so that is our atom. So we figured out that the protons and the neutrons are about the same mass. And I'm going to show you their actual masses in a second. They're about the same mass. The neutrons, though, have no charge. They're neutral, no charge. So, summarize, we have protons. Here's the charge of a proton, right? This is a coulomb. You do not need to know this number, right? But this is what the charge of an actual proton. We just call it +1 because how annoying would it be to write out this number all the time? So we simplified it and we just call it +1. So if the question is, what's the charge of a proton? Your answer, +1. Here's its mass. Again, you don't need to know this mass. That's a lot of zeros, right? If we're going to do scientific notation in a little while, but that's like 0.24 zeros, 23 zeros, and then, so this is a very, 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 very small mass. It's approximately the same as a hydrogen atom. Neutrons have no charge, but you can see if we look at this, 1.67, 1.67, 2, there's the change right there. -24 means they're about the same, almost exactly the same. So their difference in their masses are almost indetectable. So we just say because of this, that protons and neutrons have similar masses, or the same mass even. So if the question is like, who has similar masses? The answer, protons and neutrons have similar masses. Electrons. Now electrons, you look at this charge here, 1.6 times 10 to the -19th. I'm going to go back. Look at protons, 1.6 times 10 to the -19th. The charge is exactly the same. The only difference is that protons are positive and electrons are negative. So we call electrons' charge -1, right? So I'm going to go back here. Okay, so protons again, positive, same charge, you don't need to know the numbers. Electrons, negative. Okay, so let me go back to this one. Sorry, someone needed one thing here. Okay, we can go back at the end. Okay, so now, if you look at this though, this is the crazy thing. Here's the mass of an electron. See this in -28. Again, right now we haven't done these calculations, so you're like, I don't know what -28 means. It's really small. We look here, -24, right? So that's a difference of 1,000, right? So, for example, that's 1,800 times less. So let's say a car weighs 1,800 pounds, right? So a car, that would be the weight of a proton. And then a pin, we'll say like a little pin, that's the weight of an electron, right? So think of a car that's 1,800 pounds and its charge is +1. That's the proton. So it's like this massive thing with this charge of +1. But then think of the electrons. It's the mass of a little pin and it has the same charge, just opposite. So these electrons are these tiny, tiny little things that are zipping around with incredible energy and charges. And again, these electrons, J.J. Thomson figured them out by that cathode ray tube led to our television in 1897. Okay, so let's look at these. Now, this is just everything I've talked about, just summarized. You don't need to know these numbers. You do need to know these numbers. What you need to know from here is that these proton and neutron have similar masses. An electron is like 1,800 times less. So electron is much less than the protons and the neutrons. You need to know that the neutrons are neutral, the proton has a +1 charge, and the electron has a -1 charge. Okay, so summarizing all that, Rutherford used his gold foil experiment to show that the positively charged protons are in that tiny core called the nucleus, right? So electrons were J.J. Thomson, right, with the cathode ray tube. Nucleus, that was Rutherford with his gold foil experiment. And this showed, the gold foil experiment showed that the nucleus has most of the mass of an atom. And if we actually look at this, so it's kind of hard for us being in our world to kind of really see how much of a magnitude there's a difference between the proton and the electron. So most of us have seen Angel Stadium, right? Even if you haven't been to Angel Stadium, if you've ever driven on the 57, you've seen Angel Stadium. So think of it like if you had a pin, like our electron, right? But we're going to call that our nucleus now. If you had a pin and you put the nucleus on home plate in Angel Stadium, that would be the size of the nucleus. The rest of Angel Stadium would be the rest of the atom. That's how small and dense that nucleus is. And all of the mass of Angel Stadium would be on that pin on the pitching mound. So think of all of Angel Stadium, take all the mass, put it in a pin and on the pitching mound. That's the nucleus. That's how small and dense that nucleus is. And it has like 99% of the mass of the atom in that nucleus. The rest of Angel Stadium would just be those electrons zipping around like crazy. So that means that atoms are almost all empty space, right? But then your computer's solid, right? That just like kind of makes your brain hurt a little bit, right? So atoms are almost all empty space, and 99.9% of their masses are in that tiny nucleus sitting on the pitching mound of Angel Stadium. So again, that's kind of a crazy. So if you think about like a penny is 10 to the 23rd atoms. That's like 10 with like 22 zeros, right? A lot of atoms, but it's almost all empty space, right? Okay, so now we've talked about how we figured out our protons, our neutrons, and electrons, and who discovered them, and how crazy it is that atoms are mostly empty space. So now we're going to talk about how we use that information. Okay, so atomic number. So atoms differ because of the number of protons in their nucleus. Sam, yes. Yeah, chemistry makes your brain hurt, but it's fun. Okay, so now, protons. Remember, protons are in the nucleus. So what determines the identity of an atom is the number of protons in the nucleus. Like, for example, oxygen. We can breathe oxygen because of the number of protons in the nucleus. And the reason that oxygen has the properties it does is because of those number of protons in the nucleus. And the reason iron has the properties it has, it's because of those numbers of protons in the nucleus. So the number of protons gives you the identity of the atom. You can't change protons. If we change protons, we change elements. We can change neutrons, and we can change electrons, but you can't change protons, right? Okay, so now, where are protons? If you look at a periodic table, which I have an example of a periodic table, it's the whole number. So it's the one without the decimal. That's the number of protons. And again, that's what gives the identity of the element. So I have here gold. So when I see the number 79, 79 means gold. And when I say AU, AU means gold, but they're interchangeable because, again, the number of protons is what gives the element its identity. Okay, now we call this atomic number Z. I don't know why they called it Z, just to make it harder for you, but they call it a Z. And the mass number, they call A. Again, I don't know why. The mass number is just the number of protons and the number of neutrons. Or you could say it's the atomic number plus electrons, I mean plus neutrons. Okay, now, remember, when we look at this, when we look at an element, you can't change protons. Very important. You change protons, you change elements. But you can change neutrons, you can change electrons. When we change the numbers of neutrons, that's called an isotope. So an isotope is when we change neutrons. Okay, so just so you can see how we're going to write these. X is just the element symbol. So that's like gold or carbon, oxygen, right? That's the element symbol straight from the periodic table. The number on top is the mass number. And remember, the mass number is protons and neutrons. So it's like the nucleus. The one on the bottom is the atomic number. That's, again, the number of protons. So, for example, these are 3 isotopes of hydrogen. Now, how do you figure out that it's an isotope? So remember, the number on the bottom, that's the protons. The number on the top is protons plus neutrons. Isotopes, different numbers of neutrons, right? So when you look at this, I'm going to write this a little bit neater for you. And this one is just protons. If you look at this, if you just subtract those two, it's always going to give you the number of neutrons, right? So that means hydrogen, this one has 0 neutrons. If I subtract these two, this one has 1 neutron. And if I subtract these two, this one has 2 neutrons, right? So these are different numbers of neutrons or different mass numbers. So they are isotopes. Okay. Now, these are 2 isotopes of uranium. Now, we all know about nuclear energy, or know that it exists. One of these powers a nuclear power plant, right? One of these is radioactive. One of these can make an atomic bomb. The other one just chills out, does nothing, hangs out, has really no reactivity at all, right? But the only difference between these two, so if you look at these, what is the only difference between these 2 isotopes of uranium? There's only one difference. 3 neutrons. 3 neutrons. Do you remember how much a neutron weighs? It's okay, you don't need to. It's like 10 to the negative 24th grams. So if you had a scale, your scale would have to be like, let's say you weigh like 140 pounds. That means that you would have to, your scale would read 140.000000000, right? I mean, it would have a lot of what we call precision, which we'll talk about. So this very, very, very difficult to separate these 2 isotopes. That's why nuclear energy and making nuclear weapons is so incredibly hard, right? Because the difference between the one that can create bombs and make nuclear power plants and the other one is like the tiniest bit of mass. It's like literally, it's like nothing, right? But these are why these isotopes are so important. And again, how can you tell it's an isotope? You can tell it's an isotope because remember, the protons, right? The bottom one never changes. Change protons, change elements. It's the top one that changes, right? Because there's different numbers of neutrons. Okay, so let's practice with this. Again, isotope, different numbers of neutrons. Many elements have many isotopes. And if you've ever had any kind of test, like a radiology test where you made you like drink something, or they did like an MRI with contrast where they inject you with something, they're actually injecting you or making you drink radioactive isotopes, and they're measuring the radiation coming off you. There's like, if you get to 229, I'll tell you funny stories about these isotopes. But we don't have time right now. Okay, so remembering our isotope symbol, there's 2 ways we can do this. So we can use the subscript. Remember, here's our element. The top is protons plus neutrons, and the bottom is protons. So this is usually the way that you'll see an isotope symbol. Okay, so for example, this is boron. 3 different ways to see boron. So if we look at this, here's boron, B, right? You can tell that by looking at the periodic table. The whole number on the periodic table is the 5. That's the number of protons. This number you can't see on the periodic table. The mass number is not on the periodic table. The only number you can see on the periodic table is the protons. This is protons plus neutrons, right? That's our top number. We could also write that B11 because remember, boron has 5 protons. These are interchangeable. It's just like having a 5 and a boron there is just like saying boron, boron. They mean the same thing. So often we're just going to ignore that atomic number. We're going to ignore the 5 and just put boron -11. Again, this is the protons plus the neutrons, or just do B-11. So you're going to see it all 3 different ways. Here's the hydrogen, again, which I showed you. Here's the 2 neutrons of hydrogen. So if we subtract these, there's our 2 neutrons. Subtract this one, there's that 1 neutron. There's our proton and our 1 neutron. Can't see the ends because they're in red, sorry. And then these are, again, isotopes of hydrogen. And so we call this one deuterium and tritium. And if you've ever heard the term heavy water, so heavy water is just the isotope of deuterium, right? And of course, there's going to be a little bit of tritium in there. So it's just, and they call it heavy because it's heavier by 1 neutron. Okay, so now, let's practice this. So this is an element. So I want to know what element this is. And I want to know how many protons and neutrons are in it. So first of all, how can we tell what element it is? What gives the element its identity?
The charge.
Protons it has?
Protons, right. So we just count. 1, 2, 3, 4, 5. And then we look at our periodic table.
Boron.
It's boron.
It's boron. We look for the whole number 5, right? And so you can see, and this is just the nucleus bigger, by the way, easier to see. You can see there's 5 protons, and then we just count our neutrons. 1, 2, 3, 4, 5, 6. 6 neutrons. The atomic number is just the number of protons. And remember, the mass number is protons plus neutrons. So we just add these. Our mass number is 11. So Z again, YZ, I don't know why. Z is the atomic number. Neutrons, 6. The element is B because of this, tells us it's B. The mass number is the symbol A, I don't know why. 5 plus 6 means 11. And so we can write this like this, or you could have written it like this, or you could have written it like this. Again, remember that this 5 just means boron. So often, it's like this is saying the atomic number, or sorry, the mass number is 5, and this is boron, boron. So often you'll see this or this because B means 5, 5 means B. Okay. All right, so let's try another one. So in this one, I want to write it like this. Oops. Like this, B11. What would this one be? And you can type it in the chat. You can figure out which one this is. And we're going to write it just like this because it's easier to do in the chat like this. So
I don't know. I don't know what 3 is.
Lithium.
Oh, I'm unmuted.
Oh, wait, I'm unmuted. Okay.
Right, so you have to figure, your question, that was a perfect question. Okay, that you're unmuted is, what's 3? You have to look at a periodic table, but you're looking for 3. And yeah, a lot of you get it. 3 is lithium. Right, you're just looking for that whole number in the periodic table. And then you just have to count. There's 1, 2, 3, 4, right? 5, 6, 7 total things. So this would just be lithium 7. Because remember, the mass number is protons plus neutrons. And so this one would be lithium 7. We could also write it an Li. We could put the 3 down there and the 7 up here. Or we could have written it like Li and then just put the 7. And remember, the 7 is because it's always the mass number, and the mass number is protons plus neutrons. And so again, we could have written it, here's just everything we just talked about. We could have written it like, whoops. We could have written it like this, or like this, or like this, or like this. All of those would be correct.